We've talked about the shape of sampling distributions. We've talked about the spread. Now we get to talk about the center. Let's look at an example. The average weight for snowballs made by 7th graders. Always a good example. So we can take a simple random sample of 30. We get our sample mean, sample standard deviation, and of course n is 30 because we have 30 snowballs. Now, having already watched the shape video, we can identify and verify the shape of this sampling distribution. We have a one sample example. We're talking about the mean. We have an unknown population standard deviation. So we're looking at the t-distribution. We still need to verify this like we did in the shape video, but I'm going to leave that because this is the center video. Now we can also calculate the spread, right, of that sampling distribution. Right. Standard error, right, for a t-distribution. Right, we have the formula, and 7.12 grams is the spread of the distribution that we would expect. Now we have shape, t-distribution, we have spread, 7.12 grams. We can finally talk about the center. Questions about the center is, well, what value might it have? Where is it on the number line? Where is it relative to the actual population mean? Because we're talking about this sample mean, right? And actually, very important is the relationship that has with the population mean. So I'm going to just summarize t-distribution with the spread. All right, let's graph it. All right, so here's a t-distribution, and we're talking about the center of this distribution right here. Now, we have to actually think about what does the center of the sampling distribution actually represent. All right, it's the average of all the averages because every point on here represents the average of a sample mean. Right? So we have all possible sample means represented in this curve. So this is the center of all possible sample means. Now, if we're talking about all the averages, then we're essentially talking about the entire population. Right? If we average all of the averages, that's all of the individuals, all of the members of the population. Right? Which means the center of this distribution is really the population mean or the mean of the whole population. So we can summarize, right, using this, right, and say that the center of the sampling distribution is in fact equal to the population mean, and this also works for proportions as well. Now you'll notice there's a little asterisk here because this is a nice simple relationship. This little asterisk might mean where it's going to get a little complicated or there's a little bit more to the story. But let's get the symbols. Right, here we have, this is the letter mu, which generally represents mean. So if you were to read this, this is the mean of the sample means. So this left side really refers to the center of the sampling distribution. Now, without the subscript, this represents population mean. So the mean of the sample means equals population mean. And the same is true for proportions. The mean of the sample proportions is equal to the population proportion. Right? Now, let's talk about this little caveat. So the mean or center of the sampling distribution equals the population mean, but that's true only if the sample is unbiased. This is a very important term. So let's actually figure out what does unbiased mean. We can use our snowball example. We can talk about the implied population of this simple random sample of 30 snowballs. It seems to be all 7th graders everywhere, right? Is maybe one implied population. We weren't given much information really about where the sample was drawn from. All right, so we actually have just one sample of 30. Now, they could have been drawn from across the globe, which would make them representative of all 7th graders everywhere. Or perhaps they were drawn all from Bethlehem, New Hampshire. Now, New England snow is known for its high moisture content. So if all 30 were drawn from Bethlehem, New Hampshire, maybe that sample average is a little high because of that, high moisture content, probably a little bit heavier. All right. Let's draw the distribution. All right, we have our actual true population mean, right? So the global average for all 7th graders who make snowballs. And onto that, maybe we'll assume that our sample was drawn from Bethlehem, New Hampshire, which means the sample mean is going to be actually a little high. It's going to be above the population mean. That is biased. Right? There's a systematic shift that's happened which moves everything either above or below the actual population mean. So an unbiased graph would look something like this. Right, here we have our mean of sample means, the center of the sampling distribution, right lined up with the population mean. So this is what unbiased looks like. So here are some definitions. Unbiased is whatever differences there may be between the sample mean and the population, because oftentimes we would actually expect with samples differences from the population. But the reason for it is solely due to expected random behavior, that normal random variation, which always happens. Right? That's unbiased. Now, when it's biased, we have that expected random behavior, but in addition, we have one or more factors that systematically affects all of the data, which creates this shift. In practice, it's pretty hard to identify bias sometimes. Now, what are possible sources of bias? Well, what's going to create that? Now, the sample did not have the appropriate gender representation. This is our snowball example, right? Maybe it was all the boys or all the girls who made them. Between the time the snowball was made and it was weighed, some melted. The scale was simply out of calibration. Samples were taken in the late afternoon after the sun had, partially melted some of the snow. All of these are, and there are more possible sources of bias. They all break down to pretty much two categories. Either there's some design flaw, like, not good gender representation, the scale needs to be not brought inside but outside, so there's no melting. That's all design flaw. Or equipment malfunction, like the scale's out of calibration. So, when we start talking about using sample means or sample proportions as an estimator for the population parameter being the population mean or the population proportion, as long as there are no design flaws or equipment malfunctions, sample means and sample proportions are both considered unbiased estimators for the population parameter. This is pretty useful in a lot of circumstances that we're going to use later on in this unit. One example is confidence intervals, which we will talk about in another video.